So, this is what we essentially said, this consequence of magnetic buoyancy. So, if you have, and this is a direct consequence of this, the pressure balance condition, right, the fact that you the gas pressure plus the magnetic pressure has to be constant. Okay, so if you have a magnetic flux bundle immersed in an unmagnetized plasma, the gas pressure and hence the density inside the magnetic flux bundle will be lower in comparison to its surroundings. Something like this. So, suppose you have a magnetic flux bundle, and here so you have some B1, right, and outside say the medium instead of being unmagnetized, let it have some let there be another magnetic field B2, except this is a magnetic flux bundle, therefore B1 is say much larger than B2, or even I do not really have to say much larger than, there is really no need to do that. Let us just say that is larger than B2, like that. B1, so there is a flux bundle, therefore there is a concentration of magnetic field lines. So, the magnetic pressure in the magnetic field inside here this volume is larger than the magnetic field outside. Okay. Now, we know that the gas pressure P1 plus has to be equal to P2 plus B2 squared over 8 pi, where P is the P1 is the gas pressure inside and P2 is the gas pressure outside, right. Now, since B1 is greater than B2, because of this equality, P2 has to be greater than P1. Since B1 is greater than B2, P2 has to be greater than P1 in order to maintain this equality, isn't it? Now, P is equal to N K T, right, where N is the density, the gas density. Now, if the temperature inside and outside are the same, then the only way P1 can be greater than the only way P2 can be greater than P1 is if N2 is greater than N1. In other words, the density inside, the gas density inside is lower than the gas density outside, which leads, so what happens when you have a bubble, a low density bubble inside a high density, a relatively high density fluid? What happens is the low density bubble is subject to buoyant forces. This leads to buoyancy. So, this is what I meant. This leads to magnetic buoyancy. So this was one important consequence of magnetic fields, right, being embedded in fluids. We have already started talking about P1, P and B, right, magnetic pressure and gas pressure, as though there were different kinds of, P, so essentially P, the gas pressure, and B squared over 8 pi, the magnetic pressure, are on the same footing. So, it is natural to ask, it is natural to now assign a number, assign a dimensionless number. You remember we all like dimensionless numbers in fluids and MHD and everything. It is natural to assign a dimensionless number that tells you which is dominant Is the gas pressure dominant or is the magnetic pressure dominant in a given situation? And that dimensionless number is called the plasma beta, which is defined as the ratio of the gas pressure to the magnetic pressure, magnetic field pressure, right. So, plasma beta, gas pressure over magnetic pressure. That is what the plasma beta is, right. So, if the plasma beta is larger than 1, it is gas pressure dominates, and if the reverse is true, the magnetic pressure dominates, right. So, if I make a statement the plasma beta is less than 1, that means this is a magnetically dominated situation because the magnetic pressure dominates. If I make a statement that the plasma beta is larger than 1, that means this is a gas pressure dominated situation, the magnetic fields do not matter that much. So, this is a nice dimensionless number which gives you an idea of who is dominating. There are simplifications on either sides. If beta is much larger than 1 or beta is much less than 1, things are simplified. It is only in between that you have to retain all terms, the gas pressure term as well as the magnetic pressure term, right. Okay. Yeah. So, if beta is much larger than 1, that means the gas pressure is dominant, and if beta is much less than 1, it means that the magnetic pressure is dominant. However, this is different from saying which term in the equation of motion, gradient of P or this, is dominant. You see, P itself for instance, let us consider a situation where beta is much larger than 1. P itself might be larger than b squared over 8 pi. Okay, but that is saying nothing about how about gradient of P. P itself might be larger than b squared over 8 pi, but if for instance the P is not varying much with distance, if the P at a certain x is the same as the P at another x, then the gradient of P is very small. So, P itself might be large, but if the gradient of P is small, that means in the force equation you remember it is gradient of P which appears, not P, right. So, simply because the plasma beta is large, that does not mean that you can neglect the Lorentz force term in the force equation. Okay. In the force equation, what matters is gradient of P and this thing curl B cross B. So, therefore, the plasma beta is a different statement from saying that this term or that term in the force equation can be considered or neglected. This is something that one has to. It is not P itself that matters in the momentum equation. It is the gradient of P that matters. So, this is something that needs to be kept in mind very clearly. Okay. So, this was one interesting thing that I wanted to emphasize. You will see discussions of plasma beta all over the place. Everybody talks about plasma beta, which is fine, but it is important to recognize that the plasma beta says nothing about which term gradient, i.e. which term, gradient of P or curl B cross B. dominates in the momentum equation. So, this is something that needs to be kept in mind quite clearly. The plasma beta is a very useful parameter, do not get me wrong, okay. It is a very useful parameter, but simply knowing the plasma beta does not mean that you can you know which term to neglect, okay, or consider in the force equation, in the momentum equation. So, there is something that is what I meant. Now, here is another very interesting concept, that of force free fields. Okay. So, you see here is the Lorentz force J cross B or curl B cross B. Now, there are certain configurations where you can manufacture certain configurations. One can think of certain special magnetic field configurations which are arranged such that where curl of B is perpendicular, rather is parallel to B, so that curl B cross B is 0, and these kinds of configurations are called force free configurations. What kind of force free? Lorentz force free configurations, because this is J and J cross B is the Lorentz force. So, if this condition is satisfied, that means the Lorentz force is 0 and so yeah, and the Lorentz force is 0 and therefore, the Lorentz force on that volume of fluid which contains this special kind of force, this special kind of magnetic field configuration is absent. Okay. And this can happen, for instance, if you insist that the curl of B is cross B is equal to 0, that means the curl of B is in the same direction as B, right, which is to say, if this is true, if the curl of B is some scalar parameter, some scalar constant alpha times B, then curl of B is in the same direction as B, therefore curl of B cross B is equal to 0. Right. So, this alpha has to be just a simple scalar, a scalar constant. If that is the case, then you have force free fields. So, if you can manufacture, and these are very important, not merely as a theoretical curiosity, but also in important for magnetic confinement. In lab plasmas. See, you see in the lab, plasmas are manufactured to facilitate magnetic fusion. So, you want to confine the plasma to a certain region for long enough such that fusion can occur. Okay. Now, in such situations, Lorentz forces are actually a nuisance, because they make, what Lorentz forces do is that they distort the volume, they distort the element of fluid. Okay. So, you would like to engineer the magnetic field in this volume in such a fashion that the Lorentz forces are 0. In other words, you have force free fields, and if that is the case, the your little volume element remains stable at least for long enough such that fusion can occur. So, force free fields are a subject of a lot of curiosity in lab situations. Okay. So it is not merely a theoretical concept, it's a it's a very practical thing. Ideally, force free fields might never be possible to achieve, but one strives towards it. Okay. So, these kinds of configurations are important for magnetic confinement. There is also another related concept, that of potential fields. Okay. We know that the divergence of B is always equal to 0, that is, you know, that is sacred. You cannot violate that. You cannot have magnetic monopoles, and therefore the you know, magnetic field lines always have to close in on themselves. So the divergence of B is always equal to 0. But now if additionally we also demand that the curl of B is 0. Okay. In other words, if we can come up with magnetic field configuration, and these are all, you know, these are more applicable to lab plasmas, right, both these concepts. But suppose we can engineer the magnetic field such that the curl of B, in other words the current, yeah, is also equal to 0, then one can define a potential field via B equals gradient of some scalar potential, and this arises directly from here, because the curl of a gradient is always equal to 0. We know this from basic vector calculus. So this would be the B, and that is what this is, and so I introduce a negative sign here for convention purposes. So this is this, right. So now what happens is the solution for the magnetic field is given by, from here, and so since you know, the divergence of B is 0, that means I am asking that the divergence of the gradient of this one is equal to 0. In other words, the Laplacian of this is equal to 0. And you remember that mathematically we have lots and lots of situations where we have solutions to this. Okay. So this is the concept of a potential field, and this is a scalar potential. This is not the vector potential, this is not the magnetic vector potential that you saw in electrodynamics. This is different. Okay. This is a scalar potential, and the scalar potential is applicable only to very, very specific situations, only to a specific situation where we can ensure that the curl of B is 0. These are very local situations, this is not global. Okay. So in that case we can write down this kind of an equation, and we know lots of solutions to this, right. Now what is the significance of a potential field? We were talking about a situation where magnetic potential, isn't it? And so what is the significance of this? The significance of this is that the potential fields are the ones which have the minimum possible energy of all possible configurations for a given boundary condition. So for a given boundary condition, potential fields have minimum energy, and this is very important for astrophysics, and I will tell you how. Is the minimum energy configuration, right? Okay. So it is important in the following sense. Consider the solar surface, okay, where, you know, the surface of the sun, the photosphere, is where, you know, is the last visible surface. You cannot see beneath the photosphere. Okay. Now there are instruments these days called magnetometers, where you can discern, you can measure the magnetic fields on the surface of the sun, in other words on the photosphere, and you can say, you can figure out that the longitudinal magnetic field is say B1 here and B2 here, and so on and so forth. So you would have a patch of large magnetic field, and you would have a patch of low magnetic field, and so on and so forth. So this would be, say, the solar photosphere, where this would be x1 and this would be x2, for instance, and this would be the boundary conditions. So you have what this is telling you is these are the longitudinal magnetic fields that are sticking out at you. These measurements are made using the Zeeman effect and longitudinal Zeeman effect, and the Zeeman effect can only tell you something about the magnetic fields that are pointing towards you. not in the transverse direction. Okay. So, this is boundary condition. At x1 you have b1 and x2 you have b2. So, this would be a boundary condition. Now, given the boundary condition, you know that there can be many solutions. So, the question is, given these boundary conditions, what is the magnetic field configuration in the entire volume, say in the corona above the photosphere? Yeah, what is the magnetic field configuration? This is the question. Now, turns out that if you solve for a potential field, if you solve the equation with these boundary conditions, for the same boundary conditions, if I solve this one, then the solution that this phi and the magnetic field solution that this phi m will eventually give you is the one that will have the minimum possible energy of any solution. You can have many solutions with these boundary conditions, but if you solve the Laplace's equation with these boundary conditions, you are guaranteed that the solution that it gives will have the minimum possible energy, and minimum energy is something that's always sacrosanct in physics, as you know. All fields and everything in nature always likes to come back to the minimum energy configuration. Anything else is an unstable configuration. Okay. You perturb the unstable configuration, it will always like to come back to the minimum energy configuration, which is the most stable configuration. So, therefore, you are essentially kind of indirectly making the statement that the potential, so indirectly we are implying that the potential field solution is the most stable, one of the various solutions that can satisfy a given set of boundary conditions. Given a certain set of boundary conditions, of the various solutions that can satisfy those boundary conditions, the potential field solution, which is a solution to this, is the most stable one. This is the statement where we are indirectly making. In some sense, you can see why we talked about the force-free solution and the potential solution in the same breath. This is also very closely related to the concept of a force-free solution, because a force-free solution is also one where you have no extra Lorentz forces acting on them, and so that is also, you would tend to think of that as also an equilibrium solution or a stable solution. The potential field solution is another kind of equilibrium solution. Okay, an equilibrium solution in that it is the lowest energy configuration. So, it is the configuration that all other configurations will try to come down to. You perturb any other configuration, it will always try to come down to the potential field solution. Why? Because the potential field solution is the one which has the minimum energy. Okay, it is a minimum energy solution, and so these are useful concepts to keep in mind, and all of these arise from the fact that this curious way in which magnetized plasmas behave. Okay. So, when we meet next, we will take up another very important aspect of magnetized fluids, in particular magnetized fluids which are also infinitely conducting. This aspect follows directly from the induction equation that we have already seen. The name of the phenomenon that we will discuss is what is called the frozen field approximation. Okay, the fact that the field in an infinitely conducting plasma seems to be frozen into the fluid. The fluid flows one way, the field also flows the same way. The fluid, so the velocity field in some sense tells the magnetic field what to do. That is what the frozen field concept is all about. It is also often called the Alfvén flux freezing theorem, and so it bears a little bit of detailed analysis. And once we have done that, we will go on to an astrophysical application of that, to considering the phenomenon of dynamos which, as the name implies, dynamos are situations where a small seed magnetic field can be amplified. Okay, so for the time being, we will stop here. Thank you.